Okay, so today's lesson we're looking at exponential models and applications. So these are going to be the worded questions in your test, and more likely, or pretty much, I'm 100% sure, on your calculator test. So these type of modelling questions are done on the calculator because we like to use real things and the numbers become big. If you remember back to what a exponential graph looks like, so a basic exponential, doesn't it look like something like that? Yeah. So can you see how you can often have like this massive growth, isn't it? You sort of hit an area and then up you go and it's growth. So often things like bacteria and things like that. So what we're going to do, once you've got the formula, the actual hard bit of it is just getting the formula, because then once you've got that, then you just use it to answer any question they ask about it. So you can see here we have the basic exponential like formula set up here. So you would have, like, we're used to seeing y equals something blah blah blah. So what we've got here, when you see the AO, you'll see this number here and it's going to get times with something else. That is going to be your initial quantity. So you'll see that in the questions. B is going to be a positive constant, meaning it's going to be a number that doesn't change. Now, if B is greater than 1, so say B was 2 to the power of x times, so we might say we initially had 10 and then we're going to times 2 to the power of x, so B is 2. We would see, because that's greater than 1, that would be growth. If we saw B less than 1, so say I said 10 times 0.5 to the power of x, see how 0.5 is under 1, isn't it? You would see a decay. So you see the graph look like go downwards, whatever, all right? So you need to be aware of that, and T is time. So we might not have X anymore, so when we have our formula, here we would have had A against T. So T is often a time thing. So let's go have a look at our first question here. So we got the populations of rodents in Pepper Lake City is increasing exponentially. So you know when you see that, so hopefully when you're seeing this increasing exponentially, you go, great, all right, I've got to do this formula, something like that, okay? So the changes in population are given below. So find the rule, describe it, the population. So if you have a look, AO, so now remember T, so when T is 0, so when T equals 0, that is also going to be AO. That's what AO will be at T equals 0. So what's your AO here is going to be the 1,000. Can you see that? When you've got no time. Because what's T versus 0? If you look, this is like your A and this is like T. So if you think about it, if I pop that into a basic formula, so here's the basic formula. If I say, all right, the population was 1,000 equals AO, I don't know what that is, times, even if I don't know what B is, but I know T is 0. What's anything to the power of 0? 1. So can you see how you get 1,000 equals AO? Yeah? Because we know that equals 1. All right, so we know that the AO is 1,000. And we need to, so at the moment, so we can write the rule really. We can say A equals, what have we know so far that it's 1,000 BT. We don't know what B is yet. So what we can use is use another point. So we might use another point. So we'll use when T equals 1, A equals 2,000. And I'll pop that into here, this formula here. So I'm going to say 2,000 equals 1,000 times B to the power of 1. Yeah? And what is something to the power of 1?
0.
No, what's it something to the power of 1 is itself, isn't it? So couldn't I say 2,000 equals 1,000 B? Isn't that the same? Yeah? And then if I go to solve B, wouldn't it be 2,000 divided by 1,000 equals B? So what does B equal? 2. So the rodent population is doubling every time, yeah? So you've now got the rule. Sorry, it's got a bit messy here. So the rule, I'll finally write it out, is 1,000 times 2 to the power of t. There's your final rule. We've worked out what B is. Okay, so when it says find the rodent population at 7 years, so that means t equals 7. I've got a formula now. 2 to the power of t, so you'll just do 1,000 times 2 to the power of 7. And that's why I'm saying you'll have your calculators. Don't stress, I do not know that off by heart. There you go. We've got that many rodents on Pepper Lake City. Okay, at what time, so T is the question, the population, so they're saying is A equal to that. So you've got your formula, which is 1,000 times 2 to the power of T. Then I'm going to pop in that I've got 10,000 is the population, and I'm trying to find what T is. So you're just going to use your solve function on your calculator, type that in, and you'll get T equals 3.3. So at what time? So you might say at 3.3 years. Okay? So a third of a year, if you think about it, 0.3, what's a third of the year? It is 4 months. So if it was a multi-choice, maybe we'll see 3 years and 4 months. Is that the same? Yeah? So you've got to think of those things. Okay, so now we're going to look at a decay sample. So that's when your B value is less than 1. Okay, so before it was a growth, wasn't it? Because it was timesing by 2. All right. The example is radioactive decay cooling materials. So, I mean, this is why I wrote that there. That's the most common scenario that they can come up with for this. So you're probably going to see this a fair bit. So the mass of radioactive element is described by this formula here. So you guys can see that how it looks like the exponential. So here's like that B, here's like the B value, here's AO, and there's the to the power of K and T, all right? So the initial mass is 800 grams. So if you see the initial mass, you know that is, what do you think that is? MO. Yeah, good. And the mass at 15 years, so they gave you a time, yeah, when T is 15, they told you that M equals, what am I going to say? What did it equal? 200. All right. Okay, so they are asking you to find the value of, that was supposed to be MO and K. Okay, so you know what MO is. We've already worked that one out. We said MO is 800. But we need to find, can you see that little K up here in that question up there? So we'll just plug in what we know. So we're going to use this scenario to find it. So I know when the mass is 200, I've got 800, because I already knew what MO is, times 10 to the power of negative K, I don't know what K is, times T, which was 15 years. Okay, so if I've got everything there and just one thing I don't know, I can use my calculator. We don't expect you to work that out manually. You just get your calculator out. So K equals, if you do that, 0.04. Okay, find the remaining amount after 100 years. So T equals 100 They want the amount, so m's the question. So you just, now you know your whole formula because you know that everything. So you're just going to go m would equal MO, which is 800, times 10 to the power of negative k, which is negative 0.04, times 100. So what you're essentially putting into the calculator is just this bit, yeah? You just type all that out, and then you say work it out, and you get equals. Now, the calculator might type it like that, 10 to the negative 4, which is also equal to 0.08 grams. Was it measured in grams? Yeah. Okay, so and then find the time taken. So this is T becomes the question for the mass to decrease by 80%. So if you decrease something by 80%, how much do you have? 20%. Yeah, we would have 20% of it. 20% of the initial left if it's decreased by 80%. So first find out what that is. So 0.2 times the initial amount, 800 grams, equals 160 grams. So I know this is how much I've got. So therefore, I can pop that into the formula. I want to know what time it is when it's 160 grams. And I go and I've got everything else times T. So once again, you can use your solve function here, solve, comma T, and we'll get T is approximately equal to 17.47 years. That is, okay. A population of 1,000 E. coli bacteria doubles every 15 minutes. Determine the formula for the number of bacteria at time t minutes. So because it doubles every time, so you get an amount and then it doubles, then that amount doubles, that's exponential. When it's like it doubles the amount it becomes, every time it becomes something, it doubles that. That's exponential. So hopefully when you see that, so you go, all right, it's an exponential thing, so I'm going to write out what we wrote, which was this. Okay, now let's have a think about it. It said how much we had in the beginning. How much was that? 1,000. Good, 1,000. And it is giving you B. When something doubles, what are you essentially timesing it by? 2. So B equals 2, and that's because it doubles every time, yeah? What about if I said it triples? 3. What about if I said it halves? 0.5. Can you see that? So you actually might know what B is without it being so obvious. Okay, and T is going to be the time. Now, it doubles every 15 minutes. If T is time in minutes, yeah, then it's going to double. You've got to do the time divided by 15. All right, because it's not doubling every minute, it's doubling every 15 minutes. So you're going to have to divide whatever time it is by 15 for that to be the doubling happening. So in the end, if you want to change this to, their scenario, I might say population equals 1,000 times 2 to the power of T over 15. Okay, so now I've got my formula. How long will it take for the population to reach 1,000? Give your answer in the thing. So you want the population to be 1,000. So you're going to go, so P's got to equal 1,000. So we go 1,000 equals 1,000 times 2T over 15. Oh, sorry, that should be 10,000. Yeah, I was wondering 1,000. I thought that's the initial one. Sorry, that's 10,000. Thanks for picking that up, peeps.
Don't do it again.
It's on the video. All right, so 10,000. That makes sense, more sense. So now we can use solve. And, comma, t. And it says t approximately 49.8. Now it said to the nearest minute. So I'll just say when, therefore, when t equals 50 minutes, yeah? You would write that out. Okay, so then they said a biological culture contains 500,000 bacteria at 12 p.m. on Sunday. The culture increases by 10% every hour. What time will the culture exceed 4 million bacteria? All right, so we need to work out the formula. So we can see that it's increasing by an amount every time. So it increases 10% every time. So that is like an exponential. So we would have this situation again. Okay, so I'm just writing that out. And let's try and, we know it's got to follow this pattern. What does it begin with? How much does it have at the beginning?
500.
Good, so we know that's 500,000. Okay, let's work out B. If you increase something by 10%, what do you times it by? If you're increasing something by 10%, what do you times it by? 1 point? Can you see that's 1.1? If I was increasing it by 50%, how much would I times it by? 1.5. Yeah? Can you see that? Okay, so B is 1.1. So if you were, just to practice, if I was increasing it by 20%, what would I times it by? 1.2. What if I was decreasing it by 30%? What would I be timesing it by? 0.7. Can you see that? So you can work it out. Okay, so we have everything we need, and T is time in hours. Yeah? So if we said the number of culture, so I might say number of culture equals 500,000 times 1.1 to the power of t, okay? Now, they've asked when, the question was when it is 4 million. So I'll put that into the n. So n equals 4 million. So you need to remember how many zeros are in 4 million. And then you go equals this. Sorry, that's a really bad t there, but that's the t. And we're going to do solve, comma t. And we get that t is approximately 22 hours. So it's going to take 22 hours for it to increase to 4 million. Now, we are at 12 p.m. on Sunday, and they want to know. So you've got to go from 12 p.m. Sunday. You're going to add 22 hours. Where are we going to be?
10 a.m. on Monday.
Good. So it'll take us to 10 a.m. Monday. So that's your answer. Be careful not to do it. Just write 22 hours. You won't get full marks. All right.